Thank you so much for the invitation and for organizing this talk. I'm here today. I'm trying to give an overview on a subject within mathematical general relativity. In particular, I'm going to talk about the nonlinear stability of black holes. And again, this is going to be very introductory, so please don't hesitate to ask me any questions of any sort. Okay, so what's the topic of this talk is within general relativity. That, of course, is the theory of gravity invented by Einstein in 1915. And according to this theory, to general relativity, space-time, so pretty much what we want to use to describe our universe, you can think of, is a four-dimensional manifold equipped with a Lorentzian metric. So it's a metric that has signature minus plus plus plus. And it's not just any metric on any manifold. It has to satisfy what are called the Einstein fields equation, or Einstein equations, which can be written in this form. So those are equations for the curvature of this metric, right? So it's the Ricci curvature. So it's a two-tensor. So this is an equation for a two-tensor. So it's a Ricci curvature. In 3 plus 1 dimension is minus 1/2 Ricci scalar times the metric. So this combination of curvatures has to be equal to this right-hand side T. This is called the stress energy momentum tensor of our theory, and you should think of this T as encoding all the information that you want to include in your space-time, in your universe. So if you have electromagnetic fields, if you have neutrinos, if you have any particles, it's going to sit on this right-hand side, and it's going to have its own equation of motion. But it's this matter that determines how your space-time is curved through this equation, through this combination of curvatures. So this is the equation that Einstein wrote down in the more than a century ago. And what we can immediately say, we can immediately write, for example, the simplest possible example that would be a solution to this equation. That would be the Minkowski space-time. So it's nothing else than R4, when you think of it as equipped with a constant metric. So it's really like just the Euclidean metric, right? So the dx squared plus dy squared dz squared. Now you also have a constant piece with the signature, with the minus signature. So it also has a piece of minus dt squared. So of course the coordinate that has this negative signature is the time. You should think of it as being the time in your picture. So this is the space-time of special relativity. So this. T is 0. Sorry?
T is 0.
T is 0. Why?
The stress energy tensor.
Oh yes. So this is yes, right. I was getting to that.
Nothing in it.
Right. There is absolutely nothing in it. So so this is in fact not only, it's more than that. I mean, this is the space-time of special relativity. So this is the theory that Einstein developed 10 years before general relativity in 1905, and it's not only, there's nothing on that, so not only T is equal to 0 here, but it's stronger than that. In this metric, the Riemann curvature is identically 0, just like in Euclidean space, Riemann curvature is 0. So not only its trace and the trace of its trace are 0, it's really the full Riemann curvature to be 0. So this is the most trivial example we can think of, and it is a very important example, but yeah, nevertheless, it's kind of the most trivial. It's where you can do a special relativity in it. So you have a space-time where there is no matter and where there is absolutely no curvature at all. But it is very important to have this example in mind because, in particular, in Minkowski space, you can use this metric to classify the vector field, the vectors really on this R4, right? And so a vector, in general, it would be called to be time-like, null, or space-like, depending on its norm with this metric. So remember, this is not anymore a Riemannian metric, if you're used to that. So not all norms are greater or equal than 0. You can have strictly negative, equal to 0 or strictly positive norms. So if a vector is strictly as norm strictly less than 0, we call it time-like. Null, if it's equal to 0, we call it null, or otherwise space-like. And what is the significance of this classification? Well, in Minkowski space, because of the structure of this, because of this negative sign really, you can what you have associated to each point is a light cone. So you can see that the cone where this the cone that sits, really, that symmetric cone that sits here in this space time, represents the vectors that have norm with respect to this metric equal to 0. And if you think of it as being something that contains information on the speed of light. So here I didn't put the speed of light, but because I'm going to always set the speed of light to be equal to 1. But you should think that here there is a c square, dt square, associated with this dt. Then you'll see that this light cone describes precisely where the light would travel. Anything that travels at the speed of light travels along this cone. So the cones are the characteristics of the propagation of light. That's where the light would travel. And everything else, everything that goes slower than the speed of light, which according to general relativity is everything else, nothing can go faster than the speed of light, will travel along a time-like. We'll have a curve whose tangent vector is time-like. So in particular will travel inside the cone. And nothing can travel outside the cone. Nothing can have a tangent vector that goes outside the cone. So this is the picture in Minkowski space, but of course, in any manifold that has there is a Lorentzian manifold, you can have in the tangent space, you have the Minkowski space, like locally. So that's what you could have locally. You have this in all space times. You have this classification. The vectors will be time-like, null, and space-like. And you see, time-like and null vectors are the important ones, are the ones where information can travel in general relativity. So this is a very kind of the basic example, Minkowski space-time, but general relativity predicts also solutions are a bit more exciting. In particular, predicts space-times that have black holes. So what does that mean? Well, those are space-time that approach Minkowski's at infinity, so that's why we call it asymptotically flat. So you can think that outside a big ball, they will converge in some sense to the metric of Minkowski. But they contain also a region I'm going to call BH, like some black hole region. That has the following property, where that observers and signals, so anything that travels at the speed less or equal to the speed of light, cannot reach infinity, cannot reach that region that asymptotes to Minkowski. If you originated in a region called the black hole, that signal will never reach the faraway region. And how is that possible? Well, the picture you should have in mind is something like this. So as time progresses, you see time is in the vertical direction. You can think of some physical reason why a black hole exists is that you have some collapsing of matter. That's what is expected. That will collapse in a way that it will create a region that see those light cones that I showed you before, that in Minkowski space are very nice, vertical, and they're 45 degrees. In this picture, they actually get tilted towards the black hole, and there is a moment when they become tangent to the hypersurface that delimits this region, this black hole region. By the way, this hypersurface is called the event horizon. So the moment your black hole is tangent to your light cone is tangent to this hypersurface, you see that no matter how fast you go, or no matter if you try to tell your friend out here that you are along the event horizon, so you're sending a signal. So just like this light, you're sending a signal to your friend. Well, this light is traveling along the light cone, so it can only remain tangent to this region. Or if you go slower than the speed of light, you can only go inside. You will never be able to get out of it, and that's because the gravity in this region is so strong, so the curvature is so strong that the light cones are just tilted towards it. And since you're forced to travel inside the light cone, you will never be able to get out. So this region that it's black here, it's called the black hole. Of course, it's black because light cannot get out of it. So we can only see it as black. And so this is the sort of picture of it. Some more detailed pictures are what are called the Penrose diagrams. That I just want to give it a sort of an overview of what they are. Those are 1 + 1 dimensional representation of space-time. So what you should think of is that we have a 4-dimensional object. Okay, it's hard to draw. Let's just throw away 2 spatial dimensions. So you can think of let's work in spherical symmetry. Basically, that's what it is. Let's forget the theta and phi. Let's say directions if you're in some spherical coordinates, and we only have time and r. Let's say like some radial distances, and so this is what the Penrose diagrams do. And moreover, what they do, they do some conformal compactification of infinity. So instead of saying that infinity is infinitely far, now infinity is at a finite distance. So this is the representation of Minkowski is the Penrose diagram of Minkowski is this one. So you can see that time is in the vertical direction, and you can think of the radial distance is the horizontal direction. So each of these points represents a sphere. Okay, so we go back to 4 dimensions, and now the infinity has been brought at finite distance. So again, this boundary here is the end point of all the null curves that start from some finite region here. So any null cone that will travel at 45 degrees will end up is actually will end up infinitely far, but in this representation we just bring it back to a finite distance. But again, you should think this is really infinity. It's infinitely far. And here, if you put back one rotational dimension, you'll see that you'll have some sort of this kind of diamond. And what are these curves? Well, for example, if you take t equal constant, there will be for this foliation, depending on which t you're taking. The standard t will look something like this, or some reparametrization of t. But in any case, there will be curves in this Penrose diagram whose tangent vector is space-like, or whose normal vector is time-like. Okay, so those are they can be interpreted as the instants of times. And instead, the r equal constant are now vertical, so their tangent vector is time-like, or the normal vector is space-like. Okay, so this is this is how we represent black holes in a more mathematical. So this is Minkowski space, and now the same picture for a black hole is a bit different, but this region is pretty similar. So you also have some infinity that is brought at finite distance. You have some time equal constant, some r equal constant. But then what shows up is an extra region. That this is the black hole region. That is, you see, as now the property that is bounded by this. So this is actually a 3-dimensional hypersurface, but here it looks like a curve. But it's this hypersurface is null. So any signal, what I was saying before, is that if you have everything that travels at the speed of light, let's say that starts from here, it can very well fall inside the black hole. Great. But then if it tries to change its direction to get out of the black hole, it will never be able to. Because once you're here, once you're inside here, the fastest you can go is at 45 degrees. So the fastest you can go from here is here, and you're going to hit here, let's say r equals 0. So this is a representation of one specific black hole, a Schwarzschild black hole. I'm going to say a moment what this is, but it's you're gonna just go towards r equals 0. You're not getting out to r equal infinity. It's the moment you enter this region, you're not getting out of it. Okay, so this is kind of this is how we represent black holes. Are there any questions? Okay. Okay, so these are pictures, but of course, what are the actual solutions that we study as black holes? Where this is a pretty exhaustive list of the black holes that we know. In fact, there is something that is called the no-hair theorem, which is a kind of funny name, but that's how physicists call it. That in a certain sense is telling you that the ones I've written here, are the only solutions to the Einstein equation. Or yes.
Has that been proven? The no-hair?
Yeah, so it depends who you ask, right? So to physicists, yes, it's been in a certain sense. When what I'm saying is been proven. So I mean, what is being proven is that all solutions that are analytic are one of these. Now, of course, there is no reason to ask for analyticity. You should have just a smooth space-time, at least, if you want to be reasonable. And you can say, okay, what about smooth space-time? For that is not being proven. But analyticity somehow tells you that anything that is explicit, anything that you can write as sine and cosine, to be like anything that you can write down really is analytic most of the time, right? So then if something is explicit, it's probably it's one of these, but it's not really been proven, right? So, but in any case, so just to say that these are important because there are just a few of them. So in a certain sense, it's good that we can study them and kind of feel good about ourselves because we're studying kind of the general theory of black holes. And they of course the first solution that was found is called the Schwarzschild solution. So this was found just a few months. So I think this was really 2 or 3 months after Einstein wrote his Einstein equation, which is pretty impressive. You think that back then in the 1915 or 16, first of all, they had a war in Europe, and they also didn't have archive. So, but somehow Karl Schwarzschild was able to know about the Einstein equation and try to solve it, and he solved it. And to solve in particular the Einstein equation with the t equal to 0, he actually recovers. It goes back as being the Einstein vacuum equation, Ricci equals 0. Because if you take the trace of that left-hand side, you see that also the scalar curvature vanishes. So Ricci has to vanish too. And so what Karl Schwarzschild did was to work in spherical symmetry. So you have a PDE, a complicated PDE, you impose a spherical symmetry, you get an ODE. So that's basically what he did. Very smart, and it's also very easy to solve at that point. You get an ODE. When you integrate the ODE, you get a constant of integration. The constant of integration is this parameter m. Okay, so that's why there is a number. So for each m, you have a solution to the Einstein equation. That is written like this. So it's very nice. Again, so this is the spherical symmetry. You see, so this is the round metric on the sphere. And then you have your dt square and dr square, and there is this coefficient in front of it, right? So in particular, if m is equal to 0, this is Minkowski space in spherical coordinates. So if m is non-zero, you have this coefficient, and what is m? Well, if you take this metric and you compare it to the gravitational field of an isolated body of mass m according to Newtonian theory, you get something that they fit, okay, if you go like far away. So this, in a certain sense, is the general relativity equivalent of the gravitational field outside a star of mass m, okay? And so people were very, very excited. Einstein was very, very excited because this was exactly what they wanted, right? A solution that represents a star of mass m. And okay, people didn't worry too much, at least at first, about the fact that this coefficient is a bit tricky because you see it vanishes. There is an r for which this coefficient goes to 0, right? So there is 1 minus 2m over r, so r equal to m. This coefficient goes to 0, this coefficient goes to infinity. But they didn't want to think about it. They say, okay, r is greater than 2m, and that's fine. But that's where the important aspects of having then mathematicians like Lemaitre, who in the 30s, like a few years later, actually like sit down and study what's the geometry of this manifold, to realize that r equal to m is completely fine. There is nothing wrong with that hypersurface. There is nothing geometrical that's blowing up. Let's say there's nothing that's bad. It's a totally fine hypersurface. So we shouldn't cut the space-time there. It should be part of it because there is nothing that goes wrong there. And in fact, the only thing that goes wrong there is that these light cones become tangent to it. So r equal to m is precisely the location of the event horizon. That's where that region r less equal than 2m is that black hole region that's kind of weird, that if you enter, you can never get out of it. And in fact, people were so upset about it. I mean, there is a paper by Einstein in Annals of Mathematics in 1939 where he writes that this paper shows that these objects, black holes, cannot exist in reality, right? So that's which of course we know that it's not true. One of the many things that Einstein got wrong, but this doesn't matter what you got wrong as long as you get things right. So people were just could not. I mean, physicists could not accept that there was a region where light cannot escape. What does that mean? I mean, it was really hard to make sense of it. But this metric is the first solution that shows it. And importantly, it's not the last solution that showed it. So immediately after the Schwarzschild, another solution was found. It's called Rice and Norson, was found independently by these two people. And this is very similar. I didn't write it down, but it's the same expression. Now in the coefficient, you can add plus q square over r square. So it's a quadratic expression instead of a linear. And this is a solution to the Einstein-Maxwell equation. So its reach is non-zero, but it's given in terms of electromagnetic tensors that satisfies the Maxwell equations. You have now a two-parameter family of solutions where m is the mass and q can be interpreted as the charge of the black hole. Fine, so these were two solutions that for a long time those were the only solutions that they had, and they were both spherically symmetric. So there was still some hope that it was the spherical symmetry that sort of gave this region, this black hole region, was kind of caused by the spherical symmetry. So the spherical symmetry is so unnatural. You say, okay, in physical reality there is nothing that is perfectly spherically symmetric. If you perturb the spherical symmetry, the black hole will just disappear somehow. So it's there just because it's an artifact of the symmetry. Well, no, because in 1963, so much later, and the derivation is much harder. In fact, I mean, I'm not even sure. I think most people don't even know how to derive it. I mean, if you ask, because you can check that something is a solution to the Einstein equation, but to derive it is much harder. But Roy Kerr found this another solution now that also has two parameters, m and a. And if a is equal to 0, you recover the Schwarzschild. But if a is non-zero, now it's a solution that breaks the spherical symmetry, but it's only axially symmetric. So it's a solution that has only 1 degree of symmetry, like only the rotation around an axis. And so this A can be interpreted as the angular momentum of this object. And that region also has a black hole region. He also has a coefficient that just like this disappears, so vanishes at a certain point, but there is nothing bad going on at that hypersurface. And so there is a region, there is a black hole region. And then again, immediately after its extension to the Einstein-Maxwell case, it's called Kerr-Newman, was also found. So the Kerr metric has kind of given really headaches to the physicists, because now you cannot say that the black hole is only an artifact of symmetry, because okay, axially symmetric is still a symmetry, but it's much less strong than a spherical symmetry. So in fact, after this solution was found, people started taking this black holes kind of seriously. And in fact, only after the 60s and the 70s, it's now called the golden age of black hole physics, where lots of physicists was working on really trying to understand the stability properties of this, and we're going to get to that, of these objects. So I already said the word stability. Well, these solutions, of course, they were found, and they are clearly symmetric, right? And I talked about spherical symmetry, axial symmetry, but the most important symmetry that they have is not even that. The most important symmetry is the stationarity. So they do not depend on time. You can see it from this one here. The coefficients do not depend on time t. And these ones, I didn't write them down, but the coefficients are also independent of time. So here we're talking about black holes which just sit there, never change. They're always equal to themselves as time passes. So that's a very strong symmetry. And of course, you can imagine that if we had some black holes that had some dynamics in it will not be stationary. So an obvious question is to say, well, how do we understand the dynamics of these objects? How do we understand if something happens to them? And this is something that also mathematicians were fundamental in understanding. To understand the Einstein equation, if you write it as reach equals 0, it doesn't tell you much. But if you write it in a very smart way, which is in some coordinates that are called wave coordinates, so that satisfies the D'Alembert of x equals 0, it actually takes the form of a hyperbolic system of PDE. So it's a D'Alembertian operator. So this is, it's really a generalization of the wave operator minus dt squared plus Laplacian associated to the metric G. Applied to the metric G is equal to nonlinear terms in G and its first derivatives. And so it's using this formulation that Choquet-Brois in the 50s, where she was doing a postdoc in Princeton, and Einstein was around. So that's kind of funny. So she proved that any initial data set for the Einstein equation, and what is the initial data set is a three-dimensional Riemannian manifold, which is our t equals 0, and a symmetric two-tensor that it's its second fundamental form. So how this three manifold should embed in the fourth manifold. They had to satisfy some constraint equations. Any initial data will give rise to a smooth solution. This solution is well defined local in time, and this is somewhat comes from the fact that it's a wave equation. So since we have a wave equation, we can have some existence, some local in time existence. And now the question of stability is instead the question of asking what happens to long time, what happens to the long time behavior of those solutions. So we know that we can solve locally for this initial data, so for a very small interval in principle. What happens for a long interval of time? What happens for a long time? Yes?
Is this forward in time?
Yes, forward in time. Yes. You wanna solve forward in time. There are some problems in general theory you wanna solve backward in time, but in general it depends on what you do. It can be more difficult, but yeah, it's going to work forward in time. Yes. Okay, so this is the question of stability of those. So we have those stationary solutions of the Einstein equation. Those are equilibrium points for the Einstein equation. Are those stable? And maybe let me just say one trivial slide. So just I'm sure that we say something trivial. Why do we care about stability? Well, if we have equilibrium points for some mechanical system, right? What does it mean for it to be stable? Where stability, right? It's the ability to change in a controlled manner under small perturbations, right? So if we're talking about equilibrium points, let's say for example of this ball sitting on a maximum or a minimum of a hill, right? Clearly, these are both legitimate mathematical solutions. I mean, they're equilibrium points. In fact, they are points of equilibrium, but one is stable and one is unstable, right? Because if you perturb the ball in the bottom of the hill, it will start oscillating around the bottom of the hill and then go back to it. If you perturb the one on the top of the hill, it will just fall down and never go back to the original position. So in physical reality, we don't see that. We never see, right, a ball that's perfectly put on the top of the hill. Like we don't see a pendulum that it just stays upward. We only see the pendulum that is downward, right? Because in the physical reality, we'll never be able to put the ball in the exact position of the point of equilibrium. And so that's where the issue with the stability of black holes enters into place. So now we see black holes. Okay, here I'm not saying too much about the physics, but now there is empirical evidence. Black holes are observed and detected through gravitational waves, and so on and so forth. So this is the first image was depicted of a black hole. So we know that astrophysical black holes are there. I mean, they are out there. They exist. So we know that those are stable, right? Because they exist in the physical reality. But in all these computations, in all these things what people do to detect gravitational waves to do this image, physicists use the Kerr family. So that family that I didn't write down, but that explicit solution is what is used to do these computations. So now the question is, are we using a legitimate mathematical solution that is not, though, it cannot be, though, represent a physical object because it's not stable. So the proving that Kerr, that this family is stable, is at least something that should give us a peace of mind of saying, well, then maybe it makes sense to use it to represent something that exists in the physical world, because that thing has to be stable because we see it. So that's that's so the question is really, is this Kerr? The question is not, are real black holes stable? Those are, but the question is, are we using the right mathematical solution? Because it's true, it's the only explicit, but what maybe it could be, maybe we should use, maybe there's something else that it's more complicated, and that's what we should use if this one is not stable. Okay. So this is what physicists immediately realized again in the 60s and 70s. This was a crucial issue, and they worked on it for decades, proving various forms of stability, but really not the center, not the ones that I will talk about today. So this is there are different kinds of stability. So the ones that physicists, let me just step back, the ones that physicists looked at in the 70s, something that's called the mode stability. So they really looked at basically frequency decomposition to show that there are no exponentially growing modes. So there is no that instability, the terrible instability that something tells you that it's exponentially growing. Okay, but that's far from saying that something is stable. Something that was attacked by mathematicians is instead like these three kinds of stability. Let me just give you an overview of scalar stability, linear and nonlinear stability. So scalar waves, so remember the Einstein equation is a D'Alembert. So you can say, okay, what about the standard D'Alembert? Just take box of some scalar function, psi equal to 0. Okay, let's not think about the Einstein equation. Let's think about this is what they say, no, sort of the pure man's version. Then this was studied in the early 2000s and was proved to be stable, meaning if I start with initial data that is decent, I'm not going to have a blow up of the energy. Actually, the energy of the solution is bounded by the energy of initial data, and so I have pointwise decay and all the control that I want. This was done in Schwarzschild and Rice-Nordstrom, and then in Kerr and Kerr-Newman by various people. The definitive theorem was in 2014 by the firm of Wojniacki, Schlapendorf-Rothman, that they proved that this is the case for in Kerr for all range of A. So here, these two parameters A and M they represent the angular momentum and the mass. If the angular momentum is very small, you're closer to the spherically symmetric case. So if the angular momentum is larger, it's harder, and so that's why it took longer to prove that. Okay, so what is instead linear stability? If we look at the Einstein equation, it's reach equals 0. The first simplification you can do, so that's a nonlinear system of partial differential equations, you can linearize it. So you can sort of think of taking some derivative of it and evaluate it at one solution. Now this is a linear operator. And now this is, it's more difficult because now you're looking at the full system of linearized gravity. So really, you're really looking at the Einstein equation, but it's linearization. This was first proved in Schwarzschild by the firm of Wojniacki in 2016. And this is what I did in my thesis. It was for the Rice-Nordstrom case. And then there are other works. This was proved also in Kerr and Kerr-Newman. These are all very recent works. And finally, what I want to concentrate today is on the nonlinear stability, right? So the nonlinear stability is the full thing, right? So studying Ricci equals 0, okay? And here I'm putting back in the picture also the fact that Minkowski has been proved to be nonlinearly stable. This was in the 90s by Klainerman-Szeftel. And then there have been recent works on Schwarzschild by Klainerman-Szeftel, the famous also Wojniacki-Taylor, and what I'm going to say a bit more today, even though I'm going to give an overview of how you prove this kind of results in general, but it's our joint work with Klainerman-Szeftel and Shen for the nonlinear stability of Kerr for small angular momentum. So again, when A is much smaller than M. So you're in a black hole, a family of black hole that doesn't rotate very, very much, okay? It rotates slowly. Okay, so why did I put Minkowski back in the picture, and why didn't I write it here? Why is it here obvious, and why it's not obvious in nonlinear stability? Well, the linear case is kind of it's obvious in the sense that it's what, for example, if you teach a PDE class, you talk about the wave equation in Rn, you know that there is a representation formula, and so on, and we know everything about it. So that's kind of that's classical. Why is the nonlinear stability not a classical thing? Why is it difficult? So the question is this the trivial solution stable to perturbation solutions to the Einstein equation? Well, the reason it's not easy is because the nonlinear wave equations in Minkowski space are not easy. Because if you look even at something that is much simpler than the Einstein equation, just a scalar wave equation like box of psi equal dt psi squared. So this is a nonlinear scalar wave equation with some initial data. Well, you see, if you take initial data, it's epsilon. Well, if epsilon is equal to 0, by uniqueness, the solution here is 0 for all time. But if epsilon is greater than 0, this is something that John showed in the 80s, this solution will blow up in finite time. So this means that the trivial solution for this equation, that is much simpler than the Einstein equation, it's just a nonlinear scalar wave equation that I wrote down, this solution is non-stable. So really, one could say, well, that maybe perturbations of the trivial solution of the Einstein equation will also blow up. So the nonlinear stability of Minkowski is false. Well, that's, of course, that doesn't happen because of the theorem of Klainerman. But the reason it doesn't happen is precisely because the Einstein equation has a better right-hand side. The nonlinearity is fundamental. You cannot have a right-hand side of this form. It has to be of a different form. And if you've heard about this theorem, the proof of this theorem is contained in a book of 500 pages. And there are lots of tools that are used. Okay, here the image doesn't show very well, but one of the tools is a geometrical construction of the space-time. So instead of using the wave coordinates, there is a geometrical construction, in particular vector fields that are defined along the manifold. So these are there are two null directions that define. So you are in 4 dimensions. It's a Lorentzian metric. So you can think that there are 2 linearly independent vectors that are null, and these are here we're called here E3 and E4. They kind of determine, they span these light cones where the information travel. So this is fundamental to understand that you need to have something geometrical to study these problems. Then this was something was introduced by Klainerman. It was in the 80s, the vector field method, to treat these kind of equations by getting hyperbolic estimates for them. How do you find the hyperbolic system that in this case, since you're not using those wave coordinates that Choquet-Brouat had, so you don't have anymore that nice formulation with the box, what you're going to do, you're going to use the fact that the Einstein equation is equivalent to the Bianchi identities, and then you can project these quantities to these surfaces that are at the intersection of these 2 light cones. And they sort of contain their hyperbolicity. And finally, what I was saying, the fact that the bad nonlinear terms, such as dt squared, are not present. This is called the null condition. This was introduced by Klainerman in the 80s. And it roughly tells you that the right-hand side should be of the form, should be of something that vanishes if you're in a null vector. So if you have a dt square, dt psi square, you should have minus a dx psi square, so that the combination is null. This is the proof of Minkowski space. Now, what is the theorem instead of a theorem of something that I will talk about today, instead of the nonlinear stability of a black hole family? Well, the theorem, here you can pick any black hole family you want, so Schwarzschild on Kerr. In particular, I will talk mostly about our result in Kerr. But what this is saying is that general initial data sufficiently close, so you're perturbing a member of a black hole family, they will evolve according to the Einstein equation to a space-time which also has the same structure as the original black hole, so still has an infinity and an event horizon, and that asymptotes back to a member of the same black hole family as time goes to infinity. So in particular, you start with your black hole, you have your 3-dimensional Riemannian manifold on which you put initial data, and then you forget about it. You forget about your black hole. Here we are in nonlinear theory. You don't have the background anymore. You're not linearizing around the background. You only have your initial data that is similar, that is very close. It's some epsilon 0 close to your member of the black hole. You let it evolve by the Einstein equation. After many, many pages, you want to show that what you get has the same form as what you had before. So it still has an event horizon, it still has an infinity like that, and all the geometrical quantities asymptote as time goes to infinity. So if there is enough time that passes, all the geometrical quantities are converging to a very specific rate to what you had before. Okay, so this is the This is the theorem. This is the statement. Are there any questions about the statement? Okay, so this is kind of this is kind of the statement. If you've seen this kind of proofs before, unfortunately they're normally very, very long, so again like hundreds of pages in doing so. And now I'll try to give a sense of why it takes so much, like so many pages to prove something like this. So what is the setup of the proof? The setup is one of the easiest that you can think of in mathematics, which is the continuity argument. Okay, so it's a really basic tool in analysis in particular. Really the way you should think is that this evolution of the initial data is constructing as a limit of finite spacetimes, where each step is governed by a finite time that defines a sub-region of spacetime with a set of bootstrap assumptions. So let me say what do I mean by that. So really what I'm thinking here is that I have some initial data. They can be on a space-like hypersurface. They can also be on two null cones. It doesn't make a huge difference. Here there is still an infinite region, but we know how to deal with it because it's similar to stability of Minkowski space. So in most of these recent results, the initial data is set up on two null cones as opposed to a space-like hypersurface, but it doesn't matter. It's not important here. What it's important is that I have a sub-region, so I have some final time. So I have a finite region here that I'm really constructing at each step. Okay, so it's a region that is parameterized by this final time, and the continuity argument is going to be applied to a subset of the interval 0 infinity. Okay, so that, and of course we know that we have a subset which is non-empty, open and closed, is the entire interval. Okay, so that's a definition of being connected, and what B is going to be in our case is all the final times between 0 and infinity, such that two things that are called bootstrap and gauge assumptions hold by M-fin I mean this finite region. Okay, so why would this prove what I want? If I am able to prove that this is non-empty, open and closed, this is going to give me this is the entire interval. So this means that that I can cover up to all the times for which these assumptions hold. So that really this region exists for infinite time. Okay, so that T can go to infinity. So you can either think of it as a limiting sequence or as a continuity argument showing that this set is non-empty, open and closed. Okay. So this is what we have to do. We have to prove that something is non-empty, open and closed. And okay, let me say something about these two words, bootstrap and gauge. Okay, so bootstrap. Okay, I don't know about you, but I am not a native speaker. When I always heard the word bootstrap, I thought that was me. I mean, I had no idea what this word meant, to be honest. I never heard anyone who was not a mathematician or not even an analyst use this word. Apparently, there is a way of saying pull yourself up with your bootstrap. Or there is some, but I never heard anyone using it. I only heard this bootstrap assumption, bootstrap. So okay, what does that mean? Okay, this is what the dictionary says. Various ways to make use of existing resources, to raise oneself to a new situation, to modify or improve music use of what is already present, relying entirely on one's effort and resources, self-generating, self-sustaining. And that's, I think, so this self-sustaining is particularly pertinent in this case. So that's how we use this word bootstrap assumptions. Those are assumptions that are not just they're not assumptions to our theorem, right? They are assumptions inside our proof. Okay, so in our proof we assume that those assumptions hold, and then we show that they hold. So that's why they sustain themselves. We're not assuming something that it's going to be in the hypothesis of your theorem. It's something that is just in the proof. and try to then say, if you work practically what this means. But so these are the first word, the bootstrap assumption that we should have. And then the gauge. Okay, so gauge, I didn't write what the dictionary says because, okay, it gets out of the, I've heard using the word gauge by people who are not mathematicians, but even mathematicians use the word gauge in many different ways. I think everyone has their own way of thinking about gauge. Okay, for me, gauge means the following. I'm looking at the Einstein equation, okay? Ricci equals 0. Ricci is a tensor, okay? So if you're a physicist, for example, you think that a tensor is an object that has some indices and that change upon change of coordinates, like with some rules, like sort of linear algebra kind of rules. If you're a mathematician, you think a tensor is a section of a vector bundle and so on. But the point of defining tensors is something that doesn't depend on the choice of coordinates, doesn't depend on the atlas, doesn't depend on the choice of coordinates, pretty much. That's I guess the simplest way of putting it. And so that's true for the Einstein equation too. It's an equation for tensors. So if I have a solution G, anything that if I take that metric and I pull it back through any diffeomorphism, that's the same solution to me. Okay, so I cannot distinguish them. And that's what gauge is. So it means I always have to keep in mind that if I'm trying to show that something converged to the metric converged to another metric, they may be written in two very different gauges. They may still be connected. Okay, so I always have to keep in mind that I will have to prove any theorem. Any theorem will have to be proven up to the choice of gauge. Okay, that's why in this set that I have this bootstrap and gauge assumptions, and I will have to show that this set is open and is an empty, open, and closed. Okay. So what are bootstrap assumptions? Those are measured in a quantitative way. How this region, that is going to call it the bootstrap region, a region that is self-sustaining, and it will self-sustain its growth. They measure how much this region is close to the perturbed family of black holes. So really schematically there will be something like this. I'm going to assume that the soup on my finite region of some differences is bounded by a small number. Okay, what are these differences? Let's say the metric G minus the metric of my Kerr black hole. The Kerr black hole I'm thinking I will converge to. Okay, so some of these differences, the metric and also their Christoffel symbols and their curvature should be small. So I am assuming that in this region, these quantities are small. And practically, I will actually assume that they're small in a very specific way, so with some decay rates and so on and so forth. And here the solution is compared to what? It's not compared to the one I started with, but it's compared to the one I think I will converge to. And what does I think I will? It means I have to find a way of parameterizing these two parameters so that at the end I'm converging to the right one. And that's very important that this is done geometrically, because it has to evolve, it has to come out of the evolution. You cannot know it from the initial time. What is the final parameter that you're converging to? Gauge assumptions are, again, so some assumptions that you sort of you put on the way your metric looks like. So the way, if you want your pullback or your the coordinates that are using. And in this works, they're all normalized towards the future, and because that's what it's needed to work. So really, the picture is that I have some initial data. You should think of this as a size epsilon 0. And I have bootstrap assumptions of size epsilon. Okay, so those are two small numbers, and in general, epsilon 0 will be smaller than epsilon. Epsilon 0 is just as small as I want, is initial data. I have freedom on it. And then I will have some choice of gauge on the final time in most of these works. Okay, so how do I prove that this set is non-empty, open, and closed? The non-empty is kind of easy. It goes back to the initial data. Okay, I have the initial data that is of size epsilon 0, so I can, it's not obvious, but it's kind of, I can, since I have some very small initial data, I can show that t equals 0 is in this set. Okay. Now open, what does open mean? Well, for example, if you have a time in this B, the time plus delta for some most delta is also in B. Right, then how do I prove that? Well, if t is in B, it means I have a time for which bootstrap and gauge assumptions hold in the past of it, right? So in that region. Can I extend it a little bit further? Well, to extend it a little bit further, I need to here's what when we say a lot, we need to improve the bootstrap assumptions. Okay, bootstrap assumptions need to be improved. So what does it mean? It means that I'm going to use the smallness of initial data and the gauge assumptions to show that actually my bootstrap assumptions are actually less equal than a constant times epsilon 0, which is strictly smaller than epsilon. So then it means I had my bootstrap assumptions tell me that they're less equal than epsilon up to here. Well, by continuity, I can extend it a little bit. If I can improve it and say, no, if they're actually strictly less than epsilon, I can extend my space-time a little bit and still being less equal than epsilon. Okay, so this is a kind of standard like continuity argument. And then the gauge assumptions also will need to be constructed for this t plus delta. The closed, so that if I have, let's say, a sequence that converges, then the limit also belongs there. This relies on some high-order CK estimates and sort of Arzelà-Ascoli theorem to show convergence. So this is kind of easy once you have all these steps here, because you have these estimates that allow you to get convergence. So really, if you do that, if we prove that, then you have the B is the whole interval and the solution is global. So really the heart of the matter is to show that bootstrap assumptions need to be improved. That the bootstrap gets improved so that those bootstrap assumptions are really self-sustaining. I'm assuming something that is true. Okay, I'm assuming something that's less equal than epsilon, actually strictly less than epsilon, so I'm fine. Okay, so this is the heart of the matter. This is where the hundreds of pages go. So how do we improve the bootstrap assumptions? Well, we need to use the hyperbolic nature of Einstein equation. So remember the Bianchi identities, so this was used already in Minkowski spacetime. These Bianchi identities are an entangled system for all our quantities, the metric, the Christoffel symbols, the curvature. But thankfully, there are two Riemann curvature terms that stand out, that actually have some very nice properties. In particular, they vanish in Kerr, and they satisfy a wave equation that is decoupled by everything else, and they are almost gauge invariant, meaning if I change coordinates of a size epsilon, they change of a size epsilon square. So for example, in linear theory, they don't change at all. So why is this something good, and especially what is this equation that they satisfy? This is something that was found in the 70s, 1972 by Minkowski, he's a physicist. So he found that this particular, this curvature component, so here I'm contracting with two null directions, this E4 and E3, and the EA and EB instead are orthogonal to the null directions. So this particular component satisfy a wave equation that only depends on alpha, and doesn't depend, so again, linear theory only depends on alpha, so it doesn't depend on all the other curvature components, which in principle it should. And this is a D'Alembertian of this so this is a two tensor, it's a D'Alembertian plus first order derivative plus a potential. So this is what physicists in the 70s really studied and showed that there are no exponentially growing modes for these solutions. So, and that's what basically it's their statement of mode stability. And here, the strategy here will be to first improve the bootstrap assumptions for these quantities, and then use these quantities to improve the bootstrap assumptions for everything else. So how do we do that? Well, so I say in linear theory, this T alpha, so this operator is equal to 0. In nonlinear theory, this is going to be given by quadratic terms, which in general are going to be expressions of this form. Like those quantities, those differences between curvature and Christoffel symbols, that satisfy the bootstrap assumption. So somehow I hope to be able to govern these nonlinear terms by the bootstrap assumptions themselves. But it turns out that even the linear Minkowski equation, so this piece equal to 0 even, is difficult to analyze because of its first order terms. So these first order terms, nabla t and nabla phi, really killed you. And what one needs to do, and what makes, again, the hundreds of pages also, is that one needs to consider higher order quantities, in particular quantities that are at the level of 2 derivatives of this curvature. So here we're going at the level of 4 derivatives of the metric, so things are getting more and more complicated. But magically, there is a kind of a bad equation for a curvature. You take two derivatives, so you're taking two derivatives of a bad equation, you get a good equation. Something that you say you never do, you never try if you didn't know that this could work. But it actually works because there is some symmetry. So there is some relation between this operation and the curvature and metric perturbations of this black hole. So there is some magic that happens, but if you take two derivatives of this equation, you go back to something that looks like the wave equation. So it's not exactly like that, but it can be studied like the wave equation. And how do we study the wave equation? Well, let me kind of wrap up. The wave equation is kind of understood, but there are some issues in studying the wave equation in black holes. One is the fact that there are what are called trapped null geodesics. So there are null curves that are geodesics and that do not fall into the black hole and do not go to infinity. They're just stuck there. They keep rotating on some spheres. For example, in Schwarzschild, R equal 3m outside the event horizon. By the way, those are the photons that we see in the image of a black hole, right? So those are the photons that keep rotating around the black hole. But the reason why we see them, the reason why we have that picture, is because those are unstable. So after they rotate a little bit, the black hole, they actually scatter out and they reach our telescope. And so these black holes are unstable, so we can get some estimates. So there is no energy concentration there. And then there is another issue that's called the superradiance, the fact that DDT in Kerr is not time-like everywhere, but there is a region near the event horizon where it's space-like. So the energy associated to it is not positive definite. So for small a, the interaction between these two things, trapping and superradiance, is simplified and can be understood in physical space, so without taking Fourier transform. While for large a, the only proof that we know to deal with these two things, it uses frequency space, and that's why our theorem in the nonlinear proof is only valid for small a, because we don't know, if for the nonlinear picture, we don't know how to use frequency space because we don't have the symmetries anymore, so we don't know how to take Fourier transform, for example. So we want to do in physical space, but in physical space we only know how to deal with this for small a for the moment at least. Okay, so how do we what we do, we define this higher order quantity. As I said, it's a level of two derivatives of this alpha. It satisfies a nonlinear wave equation that, you see, it's not exactly box equals 0, it's box plus a bunch of other terms, but all these terms are good enough. So the first order term has good divergence properties. This is coupled to this A, so it's coupled to the lower order terms. So this equation has to be viewed coupled to the defining equation for C, and these error terms are controlled by the bootstrap assumption. So here are where the many pages go. But I'm just summarizing by saying that I'm going to use this equation to improve my bootstrap assumptions for these two quantities, these alpha and alpha bar. These two curvature components are now improved from epsilon, they're improved to epsilon 0. So now the alpha and alpha, these two quantities got their bootstrap assumptions improved, and it's pretty remarkable now that they are enough to control everything else. So let me just say how. As a preamble to gauge, because now gauge becomes important at this point, because this alpha and alpha bar are gauge invariant, but everything else is not. So I have to pick a gauge. Now I need to pick a gauge. How do I pick a gauge? So there is something that is quite interesting, is that in Kerr, remember there are these two null directions. If I take the two null directions that I should, which are the ones that diagonalize the curvature, and for example for which this alpha and alpha bar are 0 in Kerr, they are not integrable in Frobenius sense. What I mean is that there is no surface there. So it means that you have these two vectors. If you take the orthogonal space in the tangent space, this orthogonal space is not involutive. Okay, so it's not even locally, you cannot locally realize it as a tangent space of a surface. So there is no sphere effectively. Okay, so these two, this E1, E2, they actually get out of the sphere, and again, there's not even a local construction of a surface. this means that we don't have surfaces, we have horizontal distribution of two-plane fields. So this means that all the elliptic estimates that we used to do in surfaces, for example in Minkowski space or in Schwarzschild, we cannot do it anymore. But what we can do, what we have to do is to consider to constantly change from a frame that doesn't have a sphere to a frame that has spheres and do estimates there. So there is a lots of going back and forth there. And now the gauge assumptions are assumed on some final sphere and the final hypersurface. So this is the actual picture from the paper. But yeah, you should think of this as being that region that I said. It's a bootstrap region that eventually will grow into our final space-time. And this sphere, the sphere where conditions are taken, is something that's interesting is that this is unrelated to the initial condition. And so this again it's a bit technical. To improve the bootstrap assumptions, there are actually two gauges that are used. One is good for one thing, one is good for another. But the point is that there is a hierarchy of renormalized quantities that satisfy transport equation, and that allows you to just having this alpha and alpha bar, these two curvature components. With this, the right gauge, you can improve the bootstrap assumptions for all the other quantities. And maybe that's the last word about how do we know what is the final mass and what is the final angular momentum of the black hole. Where this is something that is chosen in the final sphere. So in this picture, in this final sphere here, I'm going to assume that my mass and my rotation is gonna. I'm gonna set up the final mass and rotation here, and then this sphere is gonna converge and go to infinity. So it's during the limiting process, it's gonna pick up the exact mass and angular momentum to which I'm converging to. And the definitions that I use are the quasi-local mass. This is what's called a Hawking mass, and the angular momentum. This is a novel definition. It's a curvature component of so this beta is some curvature component, and there is some special some projection, so some integral of it that is used as definition of A of our angular momentum. And what's fun is that since this sphere is totally unrelated to the initial data, when we do this initialization and we transport the values of these parameters along this final hypersurface, the foliation that you have on this sphere is actually very different from the foliation you had on the initial data. And this is because there is a shift to the center of mass frame that it also has to be taken into account. This is what in physics is called the gravitational wave recoil. Since the only gauge condition that seems to work is something that it's teleological, so it's not from the initial data, but it's from the far away. In the faraway future, but somehow it has to be reconciled to the initial data. But there is a center of mass that also changes, and that is also taken into account in this proof. So, yeah, this gives an overview of the proof. And with this, I want to thank you for your attention.
Are there any questions?
This indicates that you have a nonlinear PDE and you're successfully proving things. So there must be some kind of cancellation.
Yes.
That makes it work, because you said it might not work because you wrote down a simple thing, but that's the usual equation. X dot is x squared. It just blows up.
Right. Exactly. Yes.
And so,
yes.
But then you hope, like in the fluid equation, you would hope there's some cancellation or sequence that makes it work.
Exactly. Yes.
So can you formulate sort of abstractly what the cancellation is? Or
yeah, that's
what do you do to get the cancellation?
Yeah, that's a very good question, and there are lots of cancellation that take place. But I guess the most important is the cancellation that gives really from this, from the fact that you have this Minkowski equation for alpha, the fact that you can get an equation like this for its two derivatives. I mean, when you actually do the computations, I mean, you see that you create, of course, like again, you have an equation which has, box and first order derivative potential. You take two derivatives of it. You're going to have lots of terms. But there, most of them cancel, because we basically only have this first order term, which is very special type, like it's I dt. So it's actually it vanishes in the divergence, if you read in the divergence term. So this means that there you have like so many cancellations that if you don't know where they come from, it's really it sounds like it's magic. You don't know why would this work in fact. And they are related to the fact that it's easier to see why they cancel in Schwarzschild, because in Schwarzschild this term is not there, this term is not there. So you end up having this box minus potential equals 0, let's say, in linear theory. This is what is called the Regge-Wheeler equation. And it's called Regge-Wheeler because it was found by Regge and Wheeler when they did the metric perturbations of Schwarzschild. So they took Schwarzschild, they just wrote G is equal to G of Schwarzschild plus some delta G. Okay, and you say that this delta G satisfies an equation like this at the level of the metric, no curvature. Okay, which is it's the most natural thing. You're perturbing the metric, just perturb the metric, right? But in Kerr, when people tried to do that, they didn't find an equation for this delta G. And that's why they went to curvature, which is, it's something that you don't want to do. You don't want to go to two derivatives, right? But you have to. You go to two derivatives, they found the Minkowski equation. Basically, this process is doing the reverse. It's going back to the equation, what would have been the equation for the metric perturbations of Kerr, which is actually, but it's not decoupled though, because it's not just box of psi minus v psi equals 0. It's related to the A. So that's why physicists were not finding it, because it's not an equation for just metric perturbation. It also has curvature in it. So you cannot find it by doing brute force to the metric perturbations like they did in Schwarzschild. So. And here there are so many cancellations that happen because of this process. So I don't know if if that answers your question. But of course there are lots of cancellations for the nonlinear terms, but those are more related to what happens already in Minkowski space. So those are less surprising because Minkowski space already kind of dealt with most of the nonlinear, the problems in the nonlinear terms. Here there are lots of problems in the linear. So here there is more cancellation. For me, I feel like the cancellations in the linear part are more important than the cancellation in the nonlinear, just because the nonlinear we knew them. We kind of knew them already from Minkowski. While in Kerr this is kind of novel. This is definitely some cancellation that, I don't know, I feel like when you work in General Relativity, there is always something that doesn't work, right? So this term behave like, decay is too slow, it's never going to be able to close, but somehow you know that if something doesn't work, it's because you made a mistake, because somehow it has to work. It is because there is so much geometry, they're so geometrical, those equations are so geometrical, that somehow you always find a mistake when something doesn't work, because somehow they have to work. If you like the equation is correct, the black holes are really parameterized by the Einstein equation, and so those have to be stable somehow. It's now you're really guided by the fact that it's so geometrical that if something doesn't work, maybe you made a mistake. And at least, most of the times that's what happens. But yeah, so cancellations are huge, very important.
Any other questions?
So all your perturbations are vacuum.
Yes, here, yes.
So just what would you expect if you have some perturbation with mass, like, I don't know, some scalar field you couple? What would you expect the future?
Yeah, okay, so I can tell you what I expect in the, for example, Einstein-Maxwell equation was something I've been working on since my thesis. I did the linear stability of Rest and Nordstrom, and then I'm working on extending this proof for the Kerr-Newman case. Well, there you expect this, the same theorem, you expect the same theorem to be true, right? You expect that you will still converge to you will still be stable and so on. Now the issues will be then if you're, for example, if you have electromagnetism, for example, in the picture, you don't have this, you have a system of equations, so you don't have just one equation that describes, this is also kind of a system, but you have a system of two wave equations that are coupled together in a way that it's very unusual. In fact, they're coupled through some kind of adjoint operators on this horizontal distribution, which is kind of very, very interesting structure. So the analysis will get more complicated. Now, if you're looking at, let's say, Einstein scale, so the Einstein-Maxwell is probably the most complicated case because you have non-trivial solutions also for the Maxwell field. Like this Kerr-Newman has a charge, has an electromagnetic field, so you're perturbing something that is non-trivial. Also, also the Maxwell part is non-trivial. Well, if you're perturbing, let's say, Kerr with the Einstein scalar, now the scalar field will be trivial in the background, so there is no scalar. So it will be easier to deal than the Einstein-Maxwell case, but you would expect the same theorem to hold because we don't have an explicit solution that has also a scalar. So if we had hair, so that's what the no-hair theorem, if we had the black holes with hair, so let's say a scalar field defined on it, then it would be more complicated. But since we don't,
So that no hair thing is irrespective of a matter model?
That's a good question. So it's I think it's irrespective modulo. Any matter model that satisfies decent like conditions, like the dominant energy condition, or something that it's reasonable. It's basically says that the only three things that can parameterize a black hole is the mass, the angular momentum, and its charge. So it takes into account the Einstein-Maxwell case, but anything else it doesn't. It's not. It shouldn't be there. It's not true in higher dimensions, for example. In higher dimensions, there are different solutions, for example, in 5 dimensions, and which is, it's kind of makes us feel good about the fact that we live in 4 dimensions. This kind of gives a motivation of why we live in 4 dimensions. Like in 5 dimensions, weirder things that happen. So we're not there, but yes, but in this case, you wouldn't. You wouldn't expect like a different, but I'm not saying it would be trivial to do it. It would add complications to the analysis, but it should be somewhat related to this.
Okay, shall we take another 2?
Thank you.